Hello everyone, this is DSS Zindabad and today we are going to discuss the daily challenge of Leetcode. So the given question is pseudo-palindromic paths in a binary tree. Given a binary tree where node value are digits from 1 to 9, a path in the binary tree is said to be pseudo-palindromic if at least one permutation of the node values in the path is a palindrome. Return the number of pseudo-palindromic paths going from root node to the leaf node. Okay, so after reading the problem statement, we understand that we'll be given a binary tree, and in that binary tree, from the root node to the leaf node, we need to find a number of pseudo-palindromic paths. Now, what is a pseudo-palindromic path? It is a path, right, wherein at least one permutation of that particular path is palindromic in nature. So, suppose we've been given a tree like 2, 3, 3, 1, 1, 1, right? So suppose this is the binary tree that has been given to me, right? So what I can see is I have to find a pseudo-palindromic path, the number of pseudo-palindromic paths, right? So, and there is a condition that these paths should always start from the root node and they should end at the leaf node. So here, if I look at this, I understand that if you have something, if you start from the root, which is 2, right? And if you traverse this section of the tree, you get something like 2, 3, 3, where 2 is the root and 3 at the end is the leaf node, right? So this is one path that I have. So corresponding to this path, I can have any permutation, right? So when you talk about the permutation, it goes like you can have something like what is given 233 or 323 or 332, something like these, right? So here you see, if you consider this one, this permutation, here you can see that we can consider this permutation to be palindromic in nature. What is a palindromic string? It is basically of two kinds, that is even length and odd length. So what happens in even length is you will have something like 3, 2, 2, 3, 3. Sorry, 3, right? So here these two match and these two match. So it's an even length palindromic string, which when read from the start or the end is the same. The odd length turns out to be 3, 2, 3, which is given that these two cancel out and we have at most one character which is not being cancelled out. That means it has the frequency of only one here, right? So I understand that here I need to work something with the frequency. That means there can be at most one odd occurrence, okay? So I understand one thing, that there can be at most one odd occurrence, right? So there can be different paths in the given tree, right? One we found was 233, other can be 231, right? Now, when you look at 231 path, whatever palindromic sequences you form, any forward permutation you form, they will not be palindromic in nature because you will have certain permutations such as we have been given 231, right? You can have something like 132, 123, or so on, right? But none of them will have a palindromic, none of them would be palindrome in nature, okay? So here, why is this happening? This is happening because it is not following that at most only one character has an odd occurrence. Here, if you see all of these 2, 3, 1, they have an occurrence of 1, 1, 1. So that means there are three different characters which have an odd occurrence. But what I understand from this question is that I want at most only one odd occurrence for any character that is present. The other path that I can see is 2, 1, 1, this one, right? So when I talk about the path 2, 1, 1, so if I form its permutations, I can have something like, which is existing 2, 1, 1, or I can have 1, 2, 1, or I can have 1, 1, 2, or something else, right? So if you talk about 1, 2, 1, here again, this is palindromic in nature, right? So I understand from the possible permutations of this path which is present from the root node to the leaf node, I can have a palindromic path, right? So it is a pseudo palindromic path, and I'll increment the count and I finally return for this tree that 2 is my answer. I hope the approach is clear to you. Now, what we'll do is, let's talk about how can we code this up. So I understand that the first thing that I need to do is, I need to work with the paths from the root node to the leaf node, right? And then second thing that I understand is, I need to figure out the permutations corresponding to it, corresponding to the path. After finding the permutations corresponding to the path, right, I need to check for each permutation that is it palindromic or not, right? So for each permutation, we'll say check if palindromic or not, right? So we'll know that is it a palindrome or not, and then we can have something like a variable which is answer, and we can simply increment it and then finally result, give it as the result. So this is the brute force to solve this question. Why? Because here I'm figuring out all the paths, then corresponding to each of the paths, I'm figuring out all the possible permutations, right? So as you know that we have a binary tree, right? So there can be 2 raised to the power n time complexity for this, because you're figuring out each path from the root node to the leaf node, then you're figuring out the permutation corresponding to the path. And if you look at it, we can have as many paths as possible, right? And at point of time, the n would be the height corresponding to that tree, right? So for each permutation, then we are further having a check condition that is it palindromic or not. So we have a very, very high time complexity in this case. So let's talk about the optimal approach. What I can do is, rather than figuring out the path altogether, then checking its permutation, what I'll use is, I'll say that, see, I just made that one note that for any path to be palindromic, what did we see? We saw that if any path needs to be palindromic, there can be at most one occurrence, that is at most one odd occurrence of a number in the given path, right? So as we were dealing with it, we had something like 2, 3, 3 as the path, right? So here 3, 3 is occurring twice, 2 is occurring once. So this is the frequency of their occurrence. So at most, when you talk about at most, what does at most means? That means it is less than or equal to, right? So that means either there is no odd occurrence of only one number in the given path, or there is exactly one odd occurrence of a number in the given path, right? But when we talked about the example of 1, 2, 3, right? Here what was happening in this path is all of these numbers were occurring just once. So the frequency was just one. Hence, this condition was not being satisfied in this case. So now I'll be using this approach to optimize my above approach, that was the brute force, wherein we first computed the different paths from the root node to the leaf node. Then we figured out its possible permutation. Then on those permutations, we checked that is it a palindrome or not, which had a very, very high time complexity. Now we're coming down to a time complexity which will be linear in nature. So how will this be a linear time complexity code? We'll understand in detail with a dry run. First, let's use this approach and try coding it up, and then we'll have a dry run and a complete discussion about its time and space complexity. Okay, so this is the code, right? what I can say is I'll say let's make a solve function, right? I'll pass the root and I'll pass a count, right? So I'm creating the solve function here. I'll copy paste the tree node root and we can have something like int ampersand count. So now what happens is I'll say that the base condition is that at any point of time there is no root present, right? So that means there can't be any pseudo-palindromic path, right? So in that case, you simply return a 0. Else, what I'll say is I'll recompute the count. Now, how I am recomputing the count is I'll say count XOR equals to, and then I'll have a left shift, that is root val minus 1. Now, why did I do this? How did I do this? What is this line doing? Basically, the 17th line herein, what I am doing is I am creating a sort of a count variable, which is at any point of time keeping a track of what is the number, right? Because as we know in the given question that we know that the node's value are digits from 1 to 9 explicitly, right? So I want them to be somewhat 0 to 8 because we know that our bit mask or the bit sets, they start from the 0 index, right? So herein, see, I have root val initially 2 for this example one. So 2 minus 1 makes it 1. And when we left shift it, so we get something like 1, 0, which is 2. And then we'll take an XOR with the existing count value. So basically, this is to calculate the index, which represents the position of the bits that we need to toggle, right? And we're using XOR for the purpose of toggling. Now I'll have something like, let's call it int result, right? And we'll call the solve function. I'll pass the roots left and the count. Then I'll say now go to the right part of the root and I'll pass the count. Then I'll have an if condition. Now basically this if condition will be capturing the condition of pseudo-palindromic. So what condition is pseudo-palindromic path holding? It says that that path should begin from the root and should end at the leaf node only. So I'll say that if root left is equal to root right and the count that you have alongside it, right? If you take a bitwise AND with count minus 1, if that is equal to 0, right? So in that case, you will increment the result and you will return the result. Okay. So basically, when we talk about the condition of count and count minus 1, this is basically to check that exactly one bit is set, right? That means if you get this condition, that if we get a 0, that means whatever we have can be considered palindromic in nature, right? So herein I've utilized the bit operators for solving this problem. Let's quickly run it and see if it's working fine. Okay, there is an error. Okay, so here, let's submit it. And it is working just fine. Now, what we'll do is we'll quickly have a dry run, and I hope that you'll be able to understand that how and why I have utilized this bitwise operators. Right? If you have a good knowledge of how bit operators work, I'm sure you have got it till now. But if you don't worry. I'm going to discuss it in detail as I dry run this code. So basically, this is the code that I just wrote, right? And suppose we have this tree that has been given to us in the problem. So now I'll be doing a dry run, right? I'll be forming the recursion stack space as well as I'll be drawing the recursion tree here. So what happens is here the first call is made. So we have solve 2, 0. This is the tree node value and this is the count at any point of time. This is added into my recursion stack space and my pointer is pointing towards it, right? So when I am here in the solve function, I'll check that does my root exist. As I see that it does exist, so I'll move to the next line. Now here the count is being recomputed. So initially the count that was given to me was 0. Now I'll recompute the value of count. I'll say whatever is the root value, that is 2. Because see, I know that all these nodes will always be between 1 to 9, right? And I want to map it down to 0 to it. And I want to do that using the count and the bit operators. So what I am doing is, I am saying whatever is the value of root, that is 2, 2 minus 1 is 1, have a left shift for 1, that makes it 1, 0, and then we'll XOR. So basically, what is the property of XOR? It says that if you have the same bits, that is 0, 0, or you have something like 1, 1, in these two cases, you'll always return a 0. But if you have different bits, right, in that case, you'll return a 1. Different bits means that you have 0, 1, 1, 0, something like this, right? So this is the XOR property. So now when I XOR it, I get 0, 1, that is 2. 1, 0 is in the binary term, and when you convert it into decimal, you get a 2, right? So what I'll do is, I'll say this was the count value, update it to 1, 0. Now I'll go to the next line and I'll call this solve function. So it will go to 3, comma, it will pass the count value, which is 1, 0. Now S3, 1, 0 is added, and here also the count is updated to 1, 0, right? And my pointer in the stack is pointing towards it. Now what happens is, when I come here, I see the root is not 0, and I'll recompute the value of count, right? So now my count was 1, 0. I'll see that the value of this node is 3. So 3 minus 1 is equals to 2. And when you left shift 2, you get 1, 0, 0. We'll take an XOR of it. So you get 0 because same bits. 1, 0 different bits, you get a 1. And 0, 1 that are different bits, you get a 1. So you get 1, 1, 0. So this is 6 in terms of decimal and 1, 1, 0 in terms of binary. Here it gets updated 1, 1, 0, and even here I'll update it 1, 1, 0. After that, it will call for its left. When you come to the next line, that goes like S3, 1, 1, 0, right? This gets added here, S3, 1, 1, 0. And now my pointer is pointing towards this function. So when you are here, the root is not null. You will again compute the count value. Here the count is 1, 1, 0, right? The root val here now is 3. 3 minus 1 is 2. When you take left shift of 2, you get 1, 0, 0. So that is 0. Same bits, different bits, 1, 0. So you get 1. 1, 1, same bits, you get a 0. So you again get a value that is 2. So this gets changed to 0, 1, 0. And even here I'll change it to 0, 1, 0. Then now what you will do is, you will call, now you'll come to this function, this line, that is interest is equals to solve. So again, you will call for its left child. That means you'll come here and you're calling for its left child. As you know, it is null. So it will be null. 0, 1, 0 is 10. Now when this function call is added, your pointer is pointing towards it, right? You go here in the solve function and you see that root does not exist. So you'll simply return a 0 and you'll pop out. You are again pointing to this function call right here. So now after you have completed this solve root left, that means you've been to the left child of the third node here. You'll go to the right child, as it is also null. So you'll have S null 0, 1, 0, count is passed as it is. So when you come to the solve function, it will again return a 0. So the int rest becomes 0 plus 0. So my result here is 0. Now I will check that is the root left is equal to root right. So I can see that yes, both root left and right are null. Basically, this condition is to check that if the present node I am standing on, is it the leaf node or not, right? So basically this is telling me if a leaf node or not, right? Because it was clearly mentioned in the question that the path needs to be from the root node to the leaf node, right? So after that, we have to compute these values so as to figure out that at most only there is one odd occurrence of a number. So as you see, that here we have something like 0, 1, 0, right? And if you minus 1 from this, so you will have something like 0, 0, 1. So 0, 0, 1, you'll take an AND. What does AND says? It says that only if you have both the bits as 1, in that case you will return 1. If you have 0, 1, 1, 0, or 0, 0, in all these three cases, you have to return a 0. So 0, 1, you return 0, 1, 0, return a 0, 0, 0, return a 0. And we see that yes, it is equal to 0. So it shows that this particular path is following the conditions of being a pseudo-palindromic path. So here I'll increment the result, which was initially 0, right? It gets incremented to 1, and then we finally return it to its parent and we return a 1. So even this is done, it gets popped out. Now I am standing here on this function, that is S3, 110, right? So it says, okay, you have figured out my left child, now work with my right child. So from here, what happens is we make another call, that is S1, 110. We compute the count. Here the count that has given to me is 110, and the node value is 1. So 1 minus 1 is 0. When you take a left shift of 0, you get a 1, right? You take an XOR of this, so you get 1, 1, 1, because all of 0, 1 is a different bit. So you will get a 1, 1, 0 is a different bit. You'll get a 1, 1, 0 is again a different bit. So again a 1, right? So this gets updated to 1, 1, 1. And this is here added into the recursion stack, and now my pointer is pointing here, right? So what happens next is it will check for its left child. So S null 111 is passed. As we know, it does not have a left child, it will return a 0. It will go to its right child, S null 111, return a 0, right? So after these two calls are done, right, I'm not putting it in the recursion stack space. I hope it is clear because we have limited space. So now I am standing here. I know the result from both is 0. I'll check, is the left equal to right? It will say yes, both of them are null. So I'll say check the count value, because my count value is telling me that how many numbers have an occurrence that is odd, right? So I have 111 and I have 111 minus 1, so it gets 110. So now when you add these 1, 0, what does it give you? It gives you 0, and 1, 1 gives you 1, 1, 1 gives you 1. So you get a value that is not equal to 0, so you will not increment result. So here it means that the given path you were following, what was the given path? 2, 3, 1. It has the number in the path which have greater than one odd occurrence of a character or of a number, right? So it cannot be palindromic in nature. So I am done with this, right? I'll return its value to its parent and I'll pop it out. So again, I'm standing on S3, 110. It says I am done. You have figured out the complete left tree. So you can pop me out. Now again, I'm on the first function call that we made. That was S2, 10, right? That is the root node. So now what happens is I'll make the other call to its right kid, right? Because for that function, we had figured out till here. Now we have to figure out this section and the section below it, right? So it goes like S, we call the solve function 1, we'll pass 1, 0 here. So when you pass this, you will see the value of count. As here you can see we have only 1 as the value, right? So root val minus 1 makes it 0. And when you left shift it, when you left shift 0, you get 1. So when you XOR it, you get 1, 1, right? So it gets updated to 1, 1. Then you will call for its left child, as 1 does not have a left child. So it will be null, 1, 1, and it will return a 0. Then you will call for its right child. It is 1, 1, 1. Now again, for this root here, you will recompute the value of count, right? You already had a count that was 1, 1, right? And now you will use this statement, that is root val minus 1, that is 0. You'll left shift it by 1, you'll get a 1, and then what you'll do is you will simply take an XOR. So you'll get 0, 1. 1, 0 is something you've got, right? And then you'll call for its left child and its right child. So here I like zoom it out a little. Yes. So both of these are returning 0. And when you are here now, you see that its left child is null, its right child is also null, and you have the count value. You have the count value as 1, 0. And if you have 1, 0 minus 1, so you get 0, 1, right? So now when you AND this, you get 0, 0. So again, it shows that basically, first of all, this path is a path wherein you're starting from the root and you are standing at a leaf node. That means it is a path from root to the leaf node. And as it is giving 0, 0 as the answer, it means each of the characters which are present, right? They are satisfying the condition of having at most one number having odd occurrence, right? So that is why we'll increment the result, and here the result also comes out to be 1, right? So it comes out to be 1 here. It will be passed to its parent. 0 plus 1 makes it 1, and it will pass it to its parent, and 1 plus 1 will make it 2. And then we'll finally have the answer. So here the time complexity for this code is O of n, right? And the space complexity is k plus h. Now what is h? H will be in the worst case, k will be 9 and h is the height of the tree. Why will be k 9? Because at max we can have the, as it was given that the node can have at max 1 to 9 value, right? So I hope this was clear to you guys. Thank you so much for viewing the video till the end. If you have any doubts, we can always discuss them in the comment section. Please like, subscribe, and share. Thank you.